So, this will be short and light, especially after such a good lunch. So, let me just sort of take stock of where we started off with. We had a bunch of problems here. I'm going to say find min, max, second max, merging, sorting, some small number of problems where we had pretty tight upper and lower bound for the algorithm complexity. That we had an efficient algorithm, and we also had a proof that you can't do better, okay, at least asymptotically. So, you can do sorting in n log n time and you cannot do better. You can find the max in n minus 1 comparisons, but there is an adversary argument which says you can't do better, and so on. So, there is a tight upper and lower bounds here. Then we looked at matrix multiplication, inverse, transitive closure, and today I talked about finding diameter of a graph. Okay, I am going to add maybe another problem here. Here we have some algorithms, something better than brute force, maybe like n cubed was the algorithm for matrix multiplication. We know the naive algorithm, we can improve it 2 point something, n power 2 point something is where we stand. Diameter, we saw that it takes m times n algorithm. Okay, if m is order n, then it's n square. And can we do better is a question as we have always been interested in. And here is the quest for lower bounds or improved algorithms sort of stopped, in my opinion, for some of these problems. Once we saw that here is a range of problems where forget n cubed or n square, we can't even get n power 100 algorithm for these problems, right. So, I would say the community moved here trying to show problems NP complete, and so we do not expect a polynomial time. As I said again, polynomial time meaning not even an n power 100 algorithm for these problems. So, people started looking at how do we deal with that. There are other approaches, approximation, parameterized complexity, exact algorithms, things like that. Suddenly, in the last about 10 years, people came back to this circle and tried to show some lower bounds that you can't improve it. But again, just like as I said, showing something NP also gives a lower bound that there is no polynomial time algorithm under the assumption, what is the assumption? P is not equal to NP, right. So, under the assumption P not equal to NP, there is a lower bound that strictly more than polynomial time is required for these problems. Similarly, can we at least show some lower bound under some assumption here was the thing that got reopened, and this got reopened in the last 10 years. So, this is I am actually pointing out a course at MIT, which so just what page I am looking at. Right. So, this is a fall 2020 course at MIT by Virginia Williams and Ryan Williams, and it is called fine grained algorithms and complexity, and I am just going to run through the slides of the first lecture. Okay. So, that is the plan for the next, I do not know, half an hour, 45 minutes. So, that is what this is. Okay. So, for more details, you can always go and look at. So, I am going to add one more problem to it before we get there, which is the orthogonal vectors problem. Okay. So, your input is a list of n vectors in 0 1 power d. Okay. You can all see this, right? The screen is not hiding you. The screen is hiding it. Okay. I didn't write anything after, so it's fine, right? On that line at least. Okay. So, list of n vectors in 0 1 per d, and the question I want is, does there exist two vectors? Okay, let us call this a set in S x and y such that the inner product is 0. And what is the inner product? This is summation x I times y I. So, these are binary vectors anyway. And so, question we are interested in is, are there two vectors in this list whose inner product is 0? Okay. What would be a simple naive algorithm?
Pairwise dot product.
Yeah. How much time will that take?
NC2.
NC2, exactly, because n vectors, pick every pair and check their dot product. So, n square times d, because you are looking at, these are d dimensions, you look at this d, you would compute this sum. So, this takes, and the question I want to add is there n power 2 minus epsilon algorithm? Okay, not even d, poly in d, whatever. So, we do not know this point. Okay. Okay, let me throw another problem. Okay, I do not need that screen. So, given a list of numbers, a list or S, does there exist A, B, C in S such that A plus B plus C equal to 0? Okay, so this is called a three sum, and that is called orthogonal vector problem. Okay, you will see these notations here in the slide when how much time, how would you solve this and how much time would it take? And choose 3 would be one algorithm. Try all triples from that set, add and see whether they add up to 0. Can somebody think of a better algorithm?
I don't know the complexity of this, but
Okay.
and they can compare across the duration, they compare each other and see.
Okay, let's not get into those details, but let's use the sorting idea. So, suppose I sort step 1, sort S. Now, let us see, can I use this? It is a sorted list. I do not want this pointer moving details. Let us get high level conceptually. Suppose the list is sorted, which I can do in n log n time. Let us now think about, can I do better than n cubed? No, positive numbers, the answer would be No, it's not there. So, positive, negative, all integers. Okay. Yeah, maybe. Hmm? At the first three. No, positive, negative. So maybe that's the kind of detail you're getting into. So now, can you sort of think of an n square kind of an algorithm now? Let me give you that hint. Okay. So instead of picking triples, suppose I pick pairs, and then what can I do?
Complement in the numbers.
Exactly.
So minus of a plus b should be there.
Very nice. And how do I find that?
Um, so we
So what? Okay. So what she is saying is for all pairs a comma b, find existence of minus a plus b in the set S. If you find it, then you know that there exists a triple, right? So now how much time would this take? Why? But then that's n cubed. You're not really improving. But why should it be n? You can do better.
n square log n.
it's
Sorted. So you can do binary search, right? Pick a for every pair, add this, right? A plus b, let's say, is 25. Then I am looking for a minus 25 in the list. So look for minus 25 in the sorted list, which I can do search for minus 25 in S in binary search, because S is sorted, in log n time. So for every pair you spend log n time. Is that clear? Yes. So that's an n square log n. Can be improved from n cubed. Okay. Everybody clear? Yeah. Plus an n log n to do your initial sort, but n square log n absorbs that. So you can do this again. I mean, in all these questions, we are going to ignore the polylog term. Okay. So we are really bothered about the exponent on n. So is there a n power 2 minus epsilon polylog algorithm for this? We don't know. Okay. So there is a diameter problem on in a sparse graph, which we can do it in n square time. 3 sum problem, you can do it in n square time, because I am just going to ignore the log. And then orthogonal vectors, you can do it in n square time. Can I improve it? We don't know. Can I say some lower bounds about it? Is the question we want to address. Okay. So okay, we don't care about this gradings. Okay, what is this course about, right? How fast can we solve fundamental problems in the worst case on these kind of problems? Very important computational problems in diverse areas. So there are two canonical. Okay, so one is this K-SAT problem we saw in the morning, where you have a formula, conjunctive normal form. So it's a conjunction of clauses. Each clause has K literals, and that's why it's called K-SAT. Okay, somebody asked me what is K-SAT. Each clause has K literal. Sometimes at most K is enough, and you want to ask for the satisfiability question. This is one problem. Brute force algorithm, try all 2 power assignments, and it turns out nothing significantly better is known. So the best known algorithm for small k you can do, for 3 SAT, 4 SAT, very efficient algorithms known, but as k increases, you are stuck with more or less 2 power n. So this is one question we want to know, can you do better than 2 power n? But let us come down to some polynomially solvable problems. So longest common subsequent problem, one of the standard problems in dynamic programming you would have seen in as an example in dynamic programming. You have 2 sequences over a finite alphabet, and I want to subsequence of both strings of maximum length. It has a lot of applications, computational biology and editors and so on. And the classical algorithm is n square, nothing substantially better is known. Okay, it's a small improvement, but there is no n power 2 minus epsilon. Okay, we already know what, polynomial time is something we consider as efficient, but if n is huge, even n square is inefficient. In this world of big data, ideally we want an n log n or linear time algorithm for all problems we want, okay, or at least we want to say you can't do better than n square. So, there are points in computational geometry, given n points in the plane or any 3 collinear is sort of like that problem. Given an n node order range edge graph, what is its diameter? We saw an n square algorithm. Are we stuck? So, I mean, should we look at, see, the thing about when we moved from the first circle to the last circle is the first circle, when we are looking at sorting and min and max, we are looking at individual problems and trying to find lower bounds. But when we move to NP completeness, we were trying to relate problems and somehow, give reasons why they are all hard. They are all hard, right? We had a class of problem. So, in that sense, the question we want to ask is, are we stuck because of the same reason? Is there something common going about them? That's what we want to look at. Okay. So, NP completeness tells you cannot get polynomial time, but that's not good enough. I want to know, can I get 1.4 power n, can I get 1.1 power n kind of differences. Okay. So, the whole theory is based on some two important hypotheses, it's called, or assumptions you like unless like p not equal to np, we want to now use some other hypothesis. One is called exponential time hypothesis, which is that 3 sat cannot, I said or we said k sat for large enough k cannot be done better than 2 power n so far, and we are going to make that as an assumption that it is not possible to be improved for every epsilon. So, more precise statement is this, but roughly speaking this is saying that k sat cannot be done better than 2 power 1 minus epsilon n for any small epsilon times poly into m. M is the number of clauses. This is one big assumption we are going to use, okay, that the general k sat, by that I mean k is large, cannot be solved in something better than 2 power n. That is one assumption. Okay, maybe that assumption is enough. So, I will not even get into the other assumption now, at least for this lecture, and it is called strong exponential time hypothesis. Okay. Okay, so these are the kind of problems. Orthogonal vectors is here, diameter should be somewhere there, all pair shortest path, this 3 sum problem, a whole lot of these problems have gotten some reductions between them. I see, this says in next 2 weeks we are going to look at this, next 4 and 5 we are going to look at this, and so on and so forth. Okay, that is not what we are going to do anyway. Okay. I do not think I even need this. So, this W04 refers to some paper written by Williams. So, these are all some papers in the last 10-15 years on these problems. Okay. So, fairly recent. Okay. So, now let me get on to one reduction. So, one of the things in NP complete reductions, the reductions were taking polynomial time. We said if you solve this in polynomial time, you can solve that in polynomial time, because the reduction was polynomial time. But here we are trying to say something else. So, that way you will see that reductions will actually take a lot of time, but that is okay. Okay. So, let me start with what is it we want to show. We want to show that orthogonal vectors problem cannot be solved. I mean, or if orthogonal vectors can be solved in order n power 2 minus epsilon poly in d time, then SAT can be solved in 2 power 1 minus epsilon n poly in m. Okay, so this is sort of like we said, if clique can be solved in polynomial time, then max independent set or minimum vertex cover can be solved in polynomial time. That is the kind of thing we said. Only thing here is this, the time is slightly different in both of these things. Okay. Okay, this is what I am going to show. And there are two ways to interpret this statement, right, this theorem. One is that if you believe that SAT cannot be solved in this time, some people believe it because there has been a lot of attempt to try and improve the SAT algorithm and they have not been successful, okay, for general SAT. So, if you believe this, then you can, it follows that this cannot be, so sort of an n square is the lower bound for that orthogonal vectors. The other way to think about it is that, oh, if you want to improve SAT algorithm, try and improve this, try and show, okay. So, this is same as, if you show an NP complete problem, there are two interpretations, that maybe it is unlikely to have polynomial time algorithm, or hey, you want to solve clique in polynomial time, try and solve this in polynomial time, your favorite seemingly simpler looking problem. Okay. So, something like that. If you want to give a better algorithm for SAT, maybe work on orthogonal vectors, because that would give you this, or if you believe that this cannot be done, then that gives you a lower bound for orthogonal vector. Okay. Good. So, this is what we want to show. Okay. So, where do I start? So, I am assuming this, right, that somebody has given me a black box algorithm for orthogonal vectors, which takes these n vectors and d dimension, gives you whether there is a pair which is orthogonal in n power 2 minus epsilon time. I am going to use that to design an algorithm for SAT. Okay. So, I start with the input for SAT, which has n variables and m clauses. And what do I have to construct? From the SAT, I have to construct vectors, because I want to use this black box algorithm. So, I have to construct some vectors d dimensional for some d and use this black box and solve my SAT. Okay. Yeah. So, how am I going to do it? So, I am going to split my vertex set, variable set into two. Let us call them S1 is x1 to x n by 2. I mean, assume n is even and so on. And I am going to construct n vectors, where n is 2 power n by 2, actually 2 power n by 2 plus 1. Of dimension m each. Okay. So, that is the goal. I am going to have this huge number of vectors, And what property do I want? Well, I want to say that there is a pair of orthogonal vectors here if and only if the original SAT formula is satisfied. Okay. So, that is the kind of goal I want. So, then I can use the orthogonal vectors algorithm and get my SAT, and then we will do the running time analysis carefully. Okay. So, these vectors are going to be like this. So, I will use, okay. So, this vectors have two parts, one for S 1 and one for S 2, and each vector is of dimension m, and this corresponds to a 0 1 assignment of variables in S 1. Okay. So, I am constructing vectors here, and I said number of such vectors is 2 power n by 2 plus 1. So, for every 0 1 assignment, how many assignments are there? Because there are n by 2 variables, it will be 2 power n by 2 assignments are there. For each one, I will construct a vector, each one in S 1. Similarly, I will do it here. And what is this m dimensional vector? It is a 0 1 vector. This vector will have, okay, so I do not want to bring in too much notation here. So, let us say vector corresponding to some assignment of S 1, the ith is 0 or 1. When is it 0? This is 0 if the assignment satisfies the clause I. And 1 otherwise. Okay. Maybe oh, I think there is an example here. Why don't I use that? Okay. So, here, so I have this formula on n variables m clauses. Let us say this is my formula. Okay. I split the variables into V 1 and V 2. I called it what? S 1 and S 2. Okay. V 1 contains the first two variables, V 2 contains the second two variables. There are 4 variables. Okay. And I look at the partial assignments of V j. So, x 1 equal to 0, x 2 equal to 0, x 1. So, there are about 4 assignments for V 1. Similarly, 4 assignments for V 2. Okay. They will correspond to 4 vertices this side, 4 vertices, 4 vectors this side, 4 vectors that side. Okay. These vectors are of m dimension. I have to tell you exactly what these vectors are. Okay. So, that will tell you here. For some reason they have added a 0 1 1 0 here, ignore that. So, it is 0 the corresponding. So, it is m dimension. So, there is a dimension for each clause. There is a dimension for each clause. I am going to set that dimension of the vector to be 0 if the corresponding assignment satisfies the class and 1 otherwise. Okay. 1 does not mean that it does not satisfy, that maybe these variables are not enough, right. This clause contains a lots of variables. I take some of the variables, set them to 1 or some assignment, and if it satisfies the clause, I am going to put a 0 here, otherwise it is 1. That is how I have these vectors. Okay. So, I have this 2 power n by 2 vectors here, 2 power n by 2 vectors here. That is all. Okay. So, now a full an assignment for this entire set of variables will contain some vertex from here and some vertex from here together will constitute the assignment for all the n variables. Okay. So, now when will that be a satisfying assignment? It is a satisfying assignment if for all the clauses either that set of variables should satisfy or that this set of variables should satisfy, and when I am satisfying I am putting 0. So, either this should be 0 or that should be 0 for all the clauses, right. So, that means that pair of vertices or vectors will be orthogonal to each other, because in each dimension one of them is 0, either this is 0 or that is 0. So, if you have a satisfying assignment, then there will be a pair of orthogonal vectors, and if you do not have a satisfying assignment, then if you pick any pair, there must be one dimension in which both of them will be 1, that you are not satisfying by these classes. So, that will make sure that this set pair of vectors is not orthogonal for any pair. Okay. And I am sure I lost most of you, right. Okay. So, should I go over again if anybody has specific question?
So, there are 3 clauses here.
Yeah. So, the vector, the dimension of the vector will be 3. I think they made it 5 or something. For some reason, they added a 0, 1 and 1, 0 here, but let us ignore that for a moment. I do not know. So, there are 3 clauses here, 1, 2, 3. Yes.
When you create the instance, you don't have a 0 and 1, 0, you don't know which part the vector is corresponding to. You're having vector in a lot of vectors.
You can create them. And in fact, even make your paper problem even more specific, that I have 2 sets of orthogonal vectors, 2 sets of vectors, and check whether somebody from here and somebody from here are orthogonal. That is all.
2 ways from the same set as well.
Yeah.
They can never be orthogonal. You put those.
Ah. Why not?
Because you'll have one in the same.
No, this will make it 0, right? Oh, all of them will have 0. Okay. Thank you. Very good. Yes. Okay, so that's the point why they added the 0, 1, because for everything, everybody here, there is an extra 0, 1 added to all these vectors. That means that no pair of them will be orthogonal, because they will have this 1 in that dimension, adding to making sure that they are not orthogonal. Similarly, here we will add 1, 0 for those guys, this other side. So, no pair of them will be orthogonal. Exactly. Okay, good. So, let me try and repeat again what is said. So, what are we trying to do? Given an input for SAT, I am trying to construct a set of vectors. So, the vectors, the huge number of vectors, this is where I said our reduction is not polynomial time, because we are going to do exponential time. So, the number of vectors, so there is one corresponding to every assignment of these variables and one corresponding to every assignment of these variables. So, that number of vectors will be 2 power n by 2 plus 1, okay. And they are of m dimension, and what do I have in that m dimension? There is a dimension corresponding to a clause. So, I look at the assignment and see what are the clauses it is satisfying. Wherever it is satisfying, I put a 0, wherever it is not satisfying, I put a 1, that is all. So, I have so many different vectors. Okay. Now, if the original formula is satisfiable, then take the satisfying assignment. So, maybe x 1 equal to 1, x n by 2 to 1, maybe all these are 0 is a satisfying assignment, that corresponds to a vertex here, corresponds to a vertex here. Take those 2 vectors, I want to claim that they are orthogonal. Why are they orthogonal? Because if you take the m dimension, one of them would satisfy each of the clauses. So, in that dimension, one of them would be 0. So, when you take the inner product, it will be 0, because in every dimension somebody is a 0. So, that sum would be 0. So, if it is satisfiable, you have a pair of vectors which are orthogonal, and conversely if you have a pair of vectors which are orthogonal, first observation is that no pair of vectors here will be orthogonal because of the way we padded and constructed. No pair of vectors here will be orthogonal. So, the orthogonal vectors will be one from here and one from here. Now, you take that assignment, then that combined assignment will satisfy all the clauses because it is orthogonal. Okay, good. So, that is a reduction. Okay, it's a reduction as we have seen in the NP completeness world, except it is from a polynomial time solvable problem, because orthogonal vectors can be we are reducing to a polynomial time solvable problem, but we are spending exponential time. That is important. Somebody asked me, right, what happens if I reduce to a polynomial time solvable problem? Then you would have shown the problem is polynomial time solvable if the reduction is polynomial time. But here let us understand now, how much time have you spent, right? So, the time you would have spent. So, if I have, now let us go back to our claim in the statement. If OV can be solved in n power 2 minus epsilon poly in D, what is n? It is 2 power n by 2 plus 1. So, now we have SAT can be solved in two power n by 2, that is my n power 2 minus epsilon into poly in n, and this is basically order 2 power n into 1 minus epsilon by 2 into poly in n, which is what we wanted to show. Yeah, so that's what. So, this time for OV for some delta greater than 0 implies this for SAT, which means that strong exponential time hypothesis is false. So, if you believe this, then you have a lower bound for orthogonal vectors. Questions? Okay. Now, let us move on to the next problem we wanted to talk about, which is the diameter, finding the diameter of a sparse graph. So, what is it we want to show? If diameter of G can be solved in order n power 2 minus epsilon, then we are going to say that orthogonal vectors can be solved in which implies strong exponential time hypothesis anyway. So, this is what we are going to do. So, in other words, we are going to reduce orthogonal vectors problem to diameter finding problem, then apply the subroutine for solving diameter to solve the orthogonal vectors. Okay. Okay. So, what is given? We have input is some n vectors and we want to construct a graph such that somehow finding the diameter of the graph corresponds to existence of orthogonal vectors here. Okay. So, again it is fairly simple reduction really. Let us go through the reduction, I think it is there. So, we are going to assume that it is a sparse graph order n or n polylog kind of edges. Okay, so this from vectors I am going to construct a graph. So, this graph has a node for each vector. Okay, so there will be like n vectors, so n vertices, plus there is a node for each coordinate. So, that is like d such nodes here. Okay, so maybe draw. So, I have given n vectors. So, I will have n nodes here. And there is dimension, let us say C1, C2, CD. Why do I have two sets of vertices? Yeah, so we can even phrase the orthogonal vectors problem as you are given two sets of vectors and you ask, is there a vector here and a vector here that are orthogonal? Let's look at that version of the problem. Okay. So, then there is two sets of vectors. Now, how am I going to draw edges? First of all, there is some two extra vertices I am going to add, and y is going to be adjacent to all of these guys, x is adjacent to all of these guys, and I think x and y are both adjacent to this middle. Now, I have to tell you how the edges across are. So, I look at this is a vector, I mean this vertex corresponds to a d dimensional vector. So, I will draw an edge from this node to C I if, okay, let us call this C I, the ith coordinate is 0 and 1 otherwise. So, that means if it is 1 I do not draw an edge, if it is 0 I will draw an edge. Okay. That is my graph. From the 2n, let us say there are 2n vectors, two sets of vectors. From the 2n vectors of dimension d, I have constructed this kind of a graph. This graph has this 2n vertices plus d vertices plus 2 more vertices, and I add x to all of these side, y to all of this side, and x and y to all these vertices. Now, the edges across, this corresponds to some vector u, and if u of j, suppose it is 0, then I would add it to the Cj vertex here. Okay, that is my entire graph. Now, let us look at, remember I am trying to reduce to the diameter problem. Let us look at the maximum distance between any pair of vertices. Okay. So, if you take a pair of vertices here, what is the distance? 2, because through x there is a distance of 2. If you pick a pair of vertices here, through y the distance is 2. X and y there is distance 1, and x is adjacent to all these guys, x is adjacent, but if I want to reach a vertex here from x, the distance is 2 again, through y we can reach. Similarly, y can reach all the vertices, the distance 2. So, every pair has distance 2 except for a vertex here and a vertex here, I do not know what the distance is. Okay. If I do not have to go through these vertices, their distance will be 3, because I can go from v to x to y to that vertex. Okay. The distance is 3, but through some Ci I may be able to reach a vertex here, then that distance will be 2. Okay. When is that possible? Okay. So, let us pick a vertex here and pick a vertex here. Their distance through x y is 3, but if I have to have a distance 2, then there must be a particular j for which both of these are adjacent. Okay. And I am adding adjacency only if they are, should be 1, is it? Okay. When I add VCI, no, I think it is fine, it is fine. Okay. So, let us see if there is, if they are orthogonal, no, I think that direct graph is fine. Suppose there is a pair of vertices which are orthogonal. What does that mean? That their inner product is 0. That means there is no Cj to which both of these guys are adjacent. So, that means the diameter is, no, not 2, 3. Okay. So, what am I saying? So, if u and v are orthogonal, right, u here and v here, they are orthogonal, implies distance between u and v is actually 3, because sorry, yeah, what did I want to say? Let us okay, sorry, yeah. So, if it is 1 I am going to add, we are not 0. Okay. So, u and v are orthogonal, that means that for every coordinate either this is 0 or this is 0. So, this edge if I am adding only when there is 1, either this edge will be absent or this edge will be absent. So, their distance will be 3. So, if there exists an orthogonal pair, the distance will be 3, and if no pair is orthogonal, then for every pair there must be a Cj through which you can get there and get 2. So, the diameter is 3 if there exists an orthogonal vector, that is what this says, and is 2 otherwise. Okay. So, now you take your vectors, construct this graph, give it to your diameter algorithm and check whether it tells you 2 or 3. Depending on the answer, you know whether there is an orthogonal pair or not. Again, okay, but this is a polynomial time reduction though. Okay, but that is okay. We have we did not go to SAT. We settled in between orthogonal vectors and diameter computation. Of course, we related orthogonal vectors and SAT through an exponential time reduction. Okay. So, it is actually, I mean, maybe even if you did not follow, it is really fairly simple. Now, this is a new sort of a direction now to show lower bounds for polynomially solvable problems, because diameter is a problem where we can solve it in n square, orthogonal vectors is something we can solve it in n square time, and now we can show under the assumption that SAT cannot be solved better than 2 power n, that these problems have this kind of a lower bound. Okay. Now, as I said, this is a whole course running for 20-30 lectures. So, there is lots of recent work on trying to do, and this goes under the name fine grained complexity. So, I will encourage you to go and look at the website for this course, I mean all other similar lecture notes. Yeah, similarly, longest common subsequence, all pair shortest paths, some problems in dynamic data structures, a lot of problems who are stuck for some time now can, you can show some lower bounds using the assumption about SAT. Okay, that's all I have. I think I will stop. Any questions or comments? Otherwise, we will go for a break.